We continue with the next presentation that's given by Florian Buchholz, and the next Florian comes afterwards, by Florian Buchholz, who's a project manager at the Department of Quality Management at ISC Konstanz. And Florian will talk to us about the famous zebra cell, so a poly-zebra cell, next generation, low-cost 3D screen printed back contact cell. Florian, the floor is yours.
Yes, good morning, everyone, and let me share my presentation. So here we go. Welcome, everyone, to my presentation on our, let's say, the prospect of a poly-zebra concept, which is a next generation low-cost 3D screen printed back contact cell. So what to start with, probably have seen before those data collected by the Clean Energy Review, showing like the collection of the very high power and high efficient solar modules currently available on the market. And you can see the top of the list is making IBC solar cells, and they reach up to 22.6% efficiency. There's a little bit of heterojunction in between, but also already you can see there's an IBC from Futura-san, which is essentially a zebra solar module. So how can we get, let's say, to the top of the list, or is there any prospects on the current industrial zebra solar cell process? So that I will try to shed a little bit of light on. So we will quickly, I will quickly introduce the zebra cell concept. I'm pretty sure almost everyone has heard about it. I will then go a bit more into detail of the poly-zebra as an upgrade of the existing solar cell process. And then the biggest part of the presentation, I will share some cost calculations on what will change when we upgrade our process. And starting off with the zebra solar cell process, as you might have heard, it's a standard PV processing equipment based IBC process. It's a full back contact cell. There's a scheme on the right hand side. It features 3D interconnection technology, which is also schematically drawn. So it means we have get to the license pointer. We have a P plus N plus interdigitated pattern on the rear side. We have metal fingers going through from left to right, and we have a boost bar that is actually connecting each of those N or P regions, and to avoid shunting of the cells, there's an insulation pattern, pattern printed on every second finger. That makes the cell stringable. It can be easily half cell cut, and in addition, it's actually bifacial. So the bifaciality is not quite as high since we have all the metal on the rear side, but it's still reaching substantial bifaciality constants. So some more details on the process. This scheme has been published by Rado before. It's essentially similar to the PERC process. It just adds a couple of process steps, and you slightly use them in a different way. And it actually has been it has shown that it's working in industrial production. So in China, with our partner, the SPIC, we are currently in mass production, and they have so far reached efficiencies on average. I think these are last year's numbers, so I assume it's a bit higher now, of 23.6% on average, and top cells up to 24%. In addition, it's currently in ramp up at Valois cells in Lithuania. Those cells will be processed probably at a bit smaller quantity, so the line capacity is a bit smaller, but those cells will be dedicated for product integration. Thus, the cost structure can be slightly different. So now, what is the poly upgrade to the process? So it's ongoing development within the HighLite project. We are trying to eliminate completely the metal recombination by introducing polysilicon layers. It also improved the surface passivation. Here you can see a very early stage image of the development. We have an P+ mid region, which is P+ poly, and an N+ PSF region, some gap region. And you can see metal, screen printed metal finger for contacting. So it is making use of the full Zebra cell production equipment. It can thus be upgraded, so it's a couple of few extra process steps. It uses an identical backend process, which is nice because it features then identical module integration. So it can be used for stringing or gluing. And again, of course, it's also bifacial. The efficiency potential so far has been calculated, where it's ongoing development, it's fine-tuning of the process. We haven't quite reached those numbers yet, but we estimate we can get up to 24.5 or even 25% efficiency with that. And we also have secured some of the key IP on it. So what does that do to our process chain? So it's not quite in order, but I give some more details on the processing, which is, for example, done at Valois here in this factory. So we use essentially 2 alkaline wet benches for the wet chemistry, for the etching, with a POCL and a BBR3 diffusion furnace, tube furnace. We use standard PCVD masking and front and rear coatings. We have a couple of HF workbenches for some glass etching in between, a laser process, and more or less standard screen printing. Of course, it's a couple more steps since we have the 3D interconnection pattern, but it uses standard screen printers. So when we now go to the anticipated poly process flow, which we also use in the following calculations, it's using polysilicon depot technology for N and P+. So there we're currently assuming acceto doping, which of course translates into 2 machines, but we already have the diffusion furnaces, so that doesn't quite require much more floor space. We use the identical back end. For the calculations, we're going a bit from our best known or current standard, and we use a couple of few silver saving technology that is anticipated to take effect very soon. And the calculations numbers, they are based on this paper by Kafle from that was published only this year, and that is I think it has been used for reference quite a number of times already. So we match those numbers, we use those numbers for the sake of comparison. So coming to the some of the base assumptions for our calculations. So we use a 5 gigawatt per year cell factory. We have a silver price, which is assumed to be $700 per kilo. I checked earlier, so that is still a bit low compared to the market. So that's probably a bit higher now. The wafer price is higher than it used to be due to this wafer shortage. So for PERC, we use $60 cents, and for N-type, $66 cents per piece. The depreciation is like 7 years for equipment, 10 years for facilities, building 20 years. Factory location of been assumed Europe. CTM losses for PERC are 0.5%, and for CIPRA, poly-CIPRA 1.5%. We are calculating for 144 half-cell module. Efficiencies are shown here, so 22.5% for PERC, CIPRA currently at 23.5%, poly-CIPRA for 24.5%, and the potential of 25%. So coming to the cell cost calculations, you can see that for PERC, we calculate about $14 per watt peak on cell. That's a bit higher than probably you've seen before, but using those assumptions, I think it's fair to say. For CIPRA, we get to, hello? Yes, we get to $19.2 per watt, which is mainly coming from this big bar that is substantially bigger than for the PERC cell, that is the metal paste. So still there's room for improvement and for substantial room for cost savings there. Now coming to the poly process, and there can see that in fact the cell gets a bit more expensive per watt. The efficiency gets up, of course. That's mainly due to here some of the process equipment. We need some more floor space and so forth. But when we go to 25% as anticipated, we get to a very similar number. So in fact, per watt peak, the costs aren't substantially increased when we fully optimize this process. So this changes when we go to the module production. So here again, the PERC reference 20, and in comparison the CIPRA. So there we compare 25 cents against 30. Then for poly, we're actually no longer in such a bad position. The module BOM and so forth remain similar, and thus we actually, in fact, we reduce our costs. And of course, that goes even further, and we are approaching the PERC reference. We're not quite there, but of course, such high efficiency modules would probably in the near future not be used for utility employment. So finally, we're comparing here the cost of ownerships, and you can see, as just stated, with poly-CIPRA, we are at 25%. We're yet substantially higher still than PERC, of course. But since the efficiency is much higher, that on module level is already decreasing that number, and you get very nice high power modules. So what is the actual effect on the LCOE would be, of course, the next question. And there you can see that we did these calculations, also very similar to that Fraunhofer paper. So here you can see that for PERC, we get to those $3.21 per kilowatt. Oh, I think I've missed some of the numbers, but you read them here. So, and for the, no, sorry. Okay, so for CIPRA, we are at substantially higher value for the kilowatt hour, and for poly-CIPRA and for poly-CIPRA 25 cents, we are getting closer to utility scale compatible electricity pricing. And those are, of course, nice and low. So to sum this up, the CIPRA IBC technology has reached mass production readiness. The poly-CIPRA IBC concept is under development. We're quite confident we can reach an efficiency potential of 20 4.5%. We have a slightly higher cell cost of ownership, but in fact a reduction of the levelized cost of electricity. It's fully compatible with the Zebra IBC technology that is on the market as of now. We still need some silver reduction to get into the range of the PERC plus LCOE when we're talking about utility scale. So for example, if one of the concepts we're looking at is leaving out the boost bars and getting a direct finger connection, we can reduce the LCOE by 10%, and then we're actually in the range of PERC. Of course, those modules will be very powerful and efficient, and they can be even more efficient when we use this completely gapless configuration, as you can see on the image. So we now have a technology where we can get rid of the gaps between the cells, but also between the strings. So it's a complete active area. There's no more gaps between the cells. And of course, this technology is ideal for specialized applications such as vehicle integration or building integration. So with that, I would like to thank you for your attention, and of course, the partners in the HighLite project.
Okay, thank you, Florian. I think you used actually all your time, including that one, for questions. So please answer your questions. Please answer your questions on the chat. There are a couple. I think there are also some unanswered questions from earlier presentations. Please use that chat. I think it's a nice tool to to basically communicate with everyone. Okay, super. Thanks. So then let's